this is what I'm going to talk about. The first part is who am I, but you have just heard that. I wanted to, if you forgot what she said, here I am in a book that Vaso Michalopoulou wrote, and she has the biographies of many more interesting people there, so I can recommend that book to you. Let me go on now and talk about what I do. The original idea from this talk and what was in the newspapers was that I would talk about the theory of time. But Vasos wanted me to talk about the measurement of time, and that's what I am paid to do, is to measure it, even though I don't know what it is. It is measured with atomic stuff, atomic clocks. This is a picture of the atom as most of you see them. What the picture does not tell you is that the electrons here are spinning, and the neutron, and the neutrons in the nucleus and the protons are all spinning too. They are like little magnets spinning. If you consider the cesium atom, which we show here, it has 55 electrons. 54 of them are in shells. Even though they're spinning, some are spinning up, some are spinning down. The average spin is 0. But the 55th one is not canceled, and it has a spin. The nucleus has a spin too. And usually, and those spins can be either together or opposite each other. The laws of quantum mechanics do not allow anything else. So if the spin of the nucleus is the same way as the spin of the electron, that's a high energy state. The atom would rather have the spin of the electron being opposite to the spin of the nucleus. It could make a transition from the high energy state to a low energy state, and then it will give off that energy in the form of a microwave. The same microwaves that make popcorn in your oven. This microwave has oscillations up and down, and the definition of a second is 9,192,631,770 periods of those oscillations. So if you want to get time from the atom, you need an atomic clock that is sensitive to that radiation. You can buy them. Here are some at the Naval Observatory. If you don't have a lot of money, you could pay $75,000 and buy some of these. These atomic clocks are HP 51s. They are a good clock. One of these clocks on a bad day will jump by about 5 nanoseconds from the right time. 5 nanoseconds is 5 billionths of a second. Now, if you have more money, you could spend $250,000 and buy maser clocks, which are about 50 times better. But if you want the most accurate clocks, you can't buy them, you have to make them. Here they are. Here they are in the process of being made. What you see here is magnetic shields that are around them. They're called atomic fountains, and the best ones won't gain or lose more than 1 second in 300 million years. That's the frequency accuracy of about a part in 10 to the 16th. So it's 1 part in 1 with 16 zeros after it. There is nothing else that people have ever made that is that accurate, that can measure anything that accurately. The volt, for example, you can measure to a part in 10 to the 12th. The population of the Earth is about 7 billion, maybe it's 8 billion now. If you could measure that to a part in the 10 to the 16th, you would be measuring it to a millionth of a person. So I could brag about these because they were built under my watch as a boss. I didn't really do anything to build them. But the truth is, already clocks are being built that are 10 to 100 times more accurate. And in maybe 10 years, someone will be standing here telling you they have a clock in use, which is apart in 10 to the 18th. The first question people might ask is, why do we want these clocks? Why would somebody spend $600,000 times 4 plus the salaries of 30 people to maintain all of those things? There's many reasons, but the most important one is GPS. A GPS satellite is just an atomic clock broadcasting its time. If you're here on the Earth and you have a GPS receiver in your smartphone, it'll pick up the time from each of these satellites. The first thing your receiver will notice is that the times seem to all be wrong. That's because it takes about 1/10 of a second for the signal to get to your receiver from the satellite. Your receiver turns that argument around. It knows how fast it travels at the speed of light. If it takes 1/10 of a second to get there, then that's 30,000 kilometers away. You take the time from each of these satellites, so the GPS receiver knows how far away it is from all of those. If you know where those satellites are, and you know how far away you are from them, then you know where you are. So you need GPS needs time to run. What happens if the GPS is wrong? So in a case like this, 3 of the satellites say it's 1 o'clock. This one says is off by 1 nanosecond. In that case, because of the speed of light, your receiver will think it's 1/3 of a meter closer to it. It doesn't take many nanoseconds accumulation before this happens. So this is why they pay me. And that's the part of the talk that I added on. Now we're going to go into the main part of the talk, which is the theories of time. And I'll tell you that just because I don't know what time is, doesn't mean people don't continually ask me. So I have a definition that I came up with a long time ago. It's in the Encyclopedia Britannica. Time is that coordinate that can be most simply related to the evolution of closed systems. It seems to be circular. It really isn't. And in the course of giving a few talks, I've decided to rewrite it this way. The value of a coordinate that can be most simply related to a sequential ordering of events. This last half is in essence Aristotle's definition. This part puts a mathematical twist to it, and you will find out later in the talk why that mathematical twist is very important, in my opinion. Let me tell you what some other people said about time. St. Thomas Aquinas, 800 years ago, said, if anybody asks me, I know what time is. No, if nobody asks me, I know what time is. And if anyone asks me, then I don't know. If you read his papers, he then says, I will not pay attention to whatever anybody wrote before me because they can't be right. I'll figure it out for myself. He goes on to talk about time, and he comes up with a definition which is very much like Aristotle's. It's basically the same as Aristotle. But there are things about time that are beyond Aristotle, and I'm going to give you a quote now by Professor Wheeler of Princeton, which my Greek isn't perfect. I think Vassos may have said it already. Time is nature's way of making sure everything doesn't happen at once. Professor Wheeler says he read it on a bathroom wall, but he doesn't say if he wrote it on the wall. On the internet you can find anything, and the same quote is attributed to these 2 American comedians. Those of you who follow movie stars will know there's an awful lot of things about Woody Allen that you can find on the internet. There is a parallel quote about space. Space is nature's way of making sure everything doesn't happen to you. It's attributed to the same people, And I think it's important because it shows the symmetry of time and space. Let's go a little backwards in between these two and talk about Isaac Newton. In my opinion, he's probably the greatest scientist who ever lived. He came up with the laws of motion and the laws of gravity. Less known is that he had a concept of time, which is that time flows evenly throughout the universe. It always has, and it always will. He needed that definition of time, and he also had to invent calculus so that he could prove his laws of motion and his laws of gravity and work them out. His idea of time was not accepted universally. Leibniz, a German, argued no, time is relative, and his argument was, if time was absolute, how could God decide when to create the universe? This was taken very seriously in those days. God was a perfect being. A perfect being does not do anything without a perfect reason. So if time always was there, why did God make the universe in 4004 BC? Why didn't he make it 15 billion years ago in the past or 15 billion years in the future? He got a lot of people believing that, and he also invented calculus, and he and Newton got into a big argument about who invented it first. The truth is that this Leibniz concept of calculus is what is taught now in school. Let's jump now up to Einstein, who turned all this around. He had his own take on all this, and I'm going to walk you through now the theory of relativity in a non-mathematical way. You'll just have to take my word on the fact that all this is true. Okay, the theory came out in 1905. You can check that. He started with two things: that all observers are equivalent. That means no matter how fast you're going or what direction, you will get the same laws of physics as any other observer. And the second thing was that all observers will measure identical values for the speed of light. This was discovered about 20 years earlier, and it was a big puzzle. How can they get the same value if you're moving at different speeds? Well, Einstein answered that. He took those two and he did the math, and he saw that you could make a consistent worldview if you just changed some of your ideas. For example, he could prove that nothing could go faster than light, no matter what. But that honorable observers will disagree, and here honorable means scientists, about what is standing still and what's moving, and how long a length is. And they'll also disagree about what happened at the same time, what happened earlier, what happened later, and how fast time moves. So in order to have these two things be true, everybody be equivalent, and get the same value for the speed of light, you had to throw out everything that physics believed. But there was one saving grace for this: job security for physicists, because although space and time get mixed up, a freshman in school could easily calculate what different observers will observe using his equations. You tell the freshman how fast you're moving in what direction, and the freshman will tell you what your data will be. And what does the freshman say? If you're a stationary observer, a moving observer will think, you'll think a moving observer's yardstick shrinks. I hope the translation said meter stick. I guess I should have changed that because this is the EU. But he'll also think that the mass is greater, that it's heavier. This is where his famous equation, E equals mc squared, comes. If you have a large energy of motion, you're moving, your mass, m, gets bigger too. But more importantly for us, your time will run slow, and everything associated with time. Your clocks will run slow, your hair will turn gray less slow, everything will be running slow if you're a moving observer being observed by a stationary observer. This was proven where I work in 1971. We took 4 atomic clocks and flew them around the world. And when we came back, we found that their time had run slow compared to the clocks on the ground, exactly as Einstein had predicted. So time has a new meaning for Einstein. He's mixed up time, and if you look at the equations, he also mixes space in with time. People's perception of space changes as well. But the essence of time remained. Time is causality. By causality, I don't mean that if you're bad to a child, you will grow up to be a bad person. That is causality. I mean a more general thing. So if a spaceman lands on the moon, it has a causal effect on us even if we don't know it, because the spaceman has gravity, and that the weight of that mass of that person will be pulling us a little bit. So it has a causal effect upon us. If there's an invisible time traveler right here listening to me, then we won't know it. We'll go on, live our lives, be good or bad people, whatever. But this room will be a little bit hotter because it was here, presumably bouncing, and air atoms were bouncing off of him. So that has a causal effect too. It's any kind of influence. Einstein said, events are the same for anybody. My talking to you is an event. Different observers will give them numbers to say where they are in space and time. The numbers can be different, but the freshmen could convert back and forth. So the numbers aren't important. Even what's early or late isn't important, but this is what's important. If light had time to travel from event A to event B, then event A can influence B, and everybody will agree about which event happened first. And some will think they happened in the same place, others might not. But if light could not go from one event to the other event, event A cannot influence event B, and observers will disagree about which happened first. In other words, time order is inseparable from the order given by causality. Now, I'm going to ask you guys a question. It's an example. I want to ask you which event happened first. Event 1, Albert Einstein got the Nobel-prize in 1922. Event 2, a star exploded in the Large Magellanic Cloud. That's actually not a cloud. It's a little galaxy going around our big galaxy. It's 200,000 light years away. We saw it in 1987, but we infer it happened 200,000 years ago. So the question is, which happened first? Did the star explode first, or did Einstein get his Nobel Prize first? Anybody want to take a guess at it? Okay.
These two events happen in the one happens in the one edge of the galaxy and the other in the other edge. So maybe they happen at the same time. Or if they do not, the time in the one edge of the galaxy is not the same with the other edge.
You're right. In fact, I cheated here. I gave you a question that no matter what you answered, you would be right. But you are particularly right. So it all depends on your observer. If you're an observer sitting stationary on the Earth with Einstein here, then you would say that one happened 200,000 years earlier. Are you crazy? But if you were in a spaceship traveling at almost the speed of light towards the Earth, your space and time would be differently broken up, and you would say, no, this happened first, and that happened later. And you'd have a different idea about the actual space. You would say, yeah, Einstein was zooming along when that happened, and whereas opposed one station on the Earth would think Einstein was staying slowly or just going around the sun at a paltry 30 kilometers per second. But all observers would agree that when we saw the supernova in 1987, that was after he got the Nobel Prize. Because light had time to go. From getting the Nobel Prize, it could have bounced around and ended up at the telescope when people saw it in 1987. In other words, order of time is inseparable from causality. If you can cause it, you happen first. And we will now leave that and get on to the question of gravity. I gave away the answer there. Einstein, after he came up with his special theory of relativity, he spent 10 years trying to understand gravity. He asked, how could gravity go through empty space and pull on the apple, like Newton said? And even worse, what does it mean to pull on the moon, to go through empty space? Now, for us, it's obvious because our mothers told us that's the way it works. But when Isaac Newton came up with this, people criticized him and said, that can't possibly make sense. His answer was, it does make sense because I get the right answer. I can compute the orbits of the planets, and I can show the same force, a little bit stronger, pulls the apple down. So that was Newton's answer. Einstein's answer was a general theory of relativity. You are familiar with parts of this. Einstein realized that the special theory of relativity they had before and Newton's theory take place in a flat space. A flat space is where Euclidean geometry applies. That's the geometry Euclid came up with and which they teach you in the schools. The sum of the angles around any triangle, alpha, beta, gamma, although in America it's alpha, beta, gamma, equal 180 degrees. That's sort of the standard for Euclidean geometry. And then, in that world, things move in straight lines unless they're pulled by a force. So, gravity is a force, electricity is a force. According to Newton and according to special relativity, they can pull something and make it not go in a straight line. But Einstein came up with a different idea. What if space is not flat? What if it's curved like this shows? Then plane geometry doesn't work on there. You can't, if you add these angles, they're going to be less than 180 degrees. And you might try to go in a straight line, but you can't do it. You try to go in the straightest way possible. That's called the principle of least action. It also has another name, the law of cosmic laziness. So that was his equation of motion in a curved space. I will give you an example of an ant. This is a two-dimensional ant in a two-dimensional universe. She's trying to go in a straight line. She can't do it. She comes back to where she was. What does she think if she's a very smart ant and her name is Isaacia Newton? She thinks gravity is pulling her back. She's going in orbit. That's what she thinks. But you and Einstein know it's because she's in a curved space. So this is a place where you have two dimensions of space. You have to imagine three dimensions of space and time all being curved in some funny ways and getting mixed up a little bit with space and time, and you could get gravity. This much everybody believes in. This they may not. So now we are now leaving the area that has been proven by experiment and gets taught in school, and we're going to go to areas where different people have different opinions, and you can decide what you want to believe. So the question comes up, does relativity allow you to go backwards in time? The answer is yes, maybe. There are several configurations that allow it according to the equations, and they all tend to involve black holes and wormholes. I think you're all familiar with black holes. Here is coordinates of space and time superimposed, and you can see they get really distorted at the black hole, which goes down to an infinite singularity. If you connect two black holes, you get a wormhole. Black holes have been observed, wormholes have not. If a wormhole existed, you could go from one end of the universe to some other place in another galaxy, and you could just zip right through the wormhole. In this picture, you have to realize that the black stuff here does not exist. There's nothing there. Your whole space is what you're seeing here, your whole time in space. And so you can zip through back and forth if these wormholes exist and go quickly in space. Can you do that in time? This question was asked by the writer Carl Sagan of the physicist Kip Thorne. Kip Thorne is shown here last year announcing the discovery of gravitational radiation of two black holes coming into each other. They created disturbances in space-time, and these were discovered by a detector called LIGO in Louisiana and one in Washington State. So he's a great theorist, and he said, yes, you can do it. It's the subject of a book called Contact and a movie that was made out of it. I recommend them. Of course, I'll tell you the book is better than the movie. But and here is his recipe. Create a wiggling wormhole. Then you wait a bit, cross to the other end and get off, and then let the wormhole wiggle around, do what it wants to do. Whoops. And then you get back on, go back, and you will return home before you left. You can do that. You cannot return home before the wormhole was created. That's why you have to let it wiggle a bit. And no one can argue with his equations, but people have argued with it because they say, yes, you can. Well, you can't really do it. We don't know how to create a wormhole. But even if we did, as soon as we got inside of the wormhole, mass curve space, our bodies would distort the space-time continuum and destroy the wormhole. And there are counter arguments to that. So there is a debate whether or not this can really be done in practice. If you could do it in practice, it would lead to some contradictions and to some interesting problems. For example, the grandfather paradox. What happens if you had a time machine, go back and kill your grandfather before your father was born? There'd be no father and no you. So what sense does it make to do it? Something's wrong here. Now, Stephen Hawking considered this issue, and he came up with a very simple answer. Ohi. You just can't do it. Now, it wasn't October 28th, so we had to have a fancy name for it. The chronology protection conjecture. That means, simply, you cannot go back in time and change the present. It's not allowed. He doesn't know why it's not allowed, but it's not allowed. That doesn't mean you can't go back in time. So here's an example. For example, this is time. So here is you, or let's say it's me. I'm here. And right here, I appear from the future in a time machine, and I give myself a brilliant idea for a great invention. I come along here, I get a patent on it, and then at this point, I get in the time machine, go back and tell myself the idea. And now I continue along here and make a lot of money from my invention. Is this allowed? It doesn't violate anything. It doesn't change the past. It doesn't change the future. It's a little strange, but I think you'd agree that if it could be done, it's a great idea. And to my future self, I'm waiting for that. Now, let's make it a bit more complicated. Let's say somebody comes up to me and says, hey, Dimitri, I got this great idea. I tell him, that is a great idea. It's such a great idea that I have a patent on it. And then I get in my time machine, go back, tell myself the idea, and get the patent. And come along here, and when he says it, I've got it. Then I go off and try to make money off of it. What happens now? Do I have to get a lawyer? Probably. So let us continue now and ask some questions now. When did time start? We've already had these ideas, infinitely back in the past, or maybe at the Big Bang. There are some variations of that. It could have been when two multidimensional brains collided. A brain is sort of like membrane. If you think about it, it's not the three dimensions of space and time that we know. They might have 20, 30 dimensions. So if two of these collide in some kind of time that we don't understand, and then they create the three-dimensional universe with time that we do understand, and that could be the brain. That could be the brain and the source of the Big Bang. Now, I don't know how the translation of brains came out. If he said miala, then that might be true too. We might be somebody's science experiment, and they might have put the brains together just to see what happens. But there's another possibility too, that time just started now. This is when it began. We were created now with our memories, with dinosaur bones, the Greek economic crisis. Everything started now. And that could be all there is. How do you know? You don't know. Is it metaphysics unprovable? Not necessarily. If we continue, you'll see some cases. They ask a similar question, when will time end? Maybe it'll never end. We used to think with the Big Bang that the universe, if it had enough mass in it, might collapse back upon itself. So the universe is expanding now. It may come back, and then time might end. In fact, Hawking's said as much in one of his books. Or maybe when these two-dimensional brains separate, ripping apart the fabric of space-time. There could be a rip coming this way right now that will end everything we're doing. But if you take the laws of physics and astronomy and what we know and try to be not creative, but simply following what we believe and assuming it's right, and you have to realize that every 100 years or even every 50 years our idea of what's right changes, time will end not with a bang but with a whimper. It will slowly peter out. We know we're existing in an expanding universe, and we also know that it's expanding faster and faster. That means we are actually losing contact with the edges of the universe. It's not that things are expanding because they're moving away, it's because the space is getting bigger. So the light to go from here to some distant object, it has more and more work to do because space is getting bigger, and because light can't travel faster than the speed of light, we eventually are unable to communicate with things further out. As the acceleration of space increases, we see less and less that we can communicate with. Well, you also have to consider, in your simple belief, that everything has a lifetime. Our sun, in a few billion years, will turn into a red giant, baking the earth and boiling the oceans, and then it will collapse into a white dwarf, and it will slowly evaporate. Black holes will slowly evaporate too. This is much more than the parts in 10 to the 16th that I was telling you about. It's more like a 1 with so many zeros after it that you don't count the zeros, but you say it's 100 to the power 100 zeros after the 1, how long it will take. But it will happen, following our theories. And once that happens, you can't make a clock to measure time. There won't be any processes that are changing that could be related to time. So time will have slowly died out. We won't know exactly when. We won't be there either because we will have evaporated, but there'll be no more sense of time. Well, okay, maybe I've got something wrong there on the fundamental stuff, so let me give you another example here. Ask the question, does time have a unique direction? I'm going forward in time, I think. So let's consider this. This is my granddaughter. This is what she's going to look like when she becomes the first Greek-American president. And that's what she's going to look like when I'm not around to see her. So that all seems to make a fine sequence. No one can argue with it. But what if I tell you time is going backwards? What's wrong with that picture? Well, you'll say, well, wait a minute. She's got wrinkles. She doesn't. This one has memories of being young, no memories of being old. So obviously, time was going the other way. But no, that isn't right. If time is going backwards, as this woman gets younger, she will lose her memories of being old. This is not Alzheimer's. This is just time is going backwards, her wrinkles disappear. Oops, and time really went backwards there. Did I do that? Okay. Yeah. So you lose your memories too. And by the time you get here, going backwards, she's lost all memories of that. There's nothing in the laws of physics that we know that can contradict this way. Now I'm going to jump to quantum mechanics, and I'm not going to tell you a lot about quantum mechanics. The next lecture will be about the quantum mechanical mind, so maybe this will help the next speaker a little bit. What is quantum mechanics? Well, it started from the discovery that you cannot measure the position of something and its speed or momentum exactly at the same time. If you could measure the speed of something, the position of something perfectly, you know nothing about its momentum or its velocity. If you know its velocity perfectly, you don't know anything about where it is. Now, you can, if you don't have perfect thing, you just have an uncertainty and an error. Those errors have to be greater than something called Planck's constant, which is a very small number, which is why we don't really see it in our everyday life. 6 times 10 to the minus 26. So that's a decimal point, 26 zeros and a 6. We know this is true. We've done many experiments on that level, and it has other variations as well. This is all called complementarity. There's a play called Copenhagen that goes around, and it's based on exploring these ideas. Maybe it's come to Athens, I don't know. Copenhagen is a city where Niels Bohr lived, and he worked all this stuff out in the early 1900s. The complementary thing is that the energy uncertainty times the time uncertainty has to be greater than Planck's constant too. So the energy uncertainty is how well you know the energy, and the time uncertainty is how long you've taken to measure it. So if you haven't taken a lot of time to measure it, you're going to have a very large unknown in your uncertainty of your energy. The person who invented complementarity thought this applied all over the place to everything, that every variable had one that was complementary to it, and you could not specify both. So they asked him, what is complementary to truth? And he had an answer: clarity. So if you can tell the truth perfectly, you're very obscure. If you want to be simple and be very clear, then you've gone very far from the truth. That's not the subject of my talk, though. Let's go on with quantum mechanics. Another principle of this was unpredictability. You would think that if you flipped a coin and you were a really good scientist and you knew the air pressure, the humidity of the air, how much the coin had been flipped, you could predict whether it would come out heads or tails. The answer is no. In quantum mechanics, you cannot do it. There's no way to predict anything to 100% accuracy. You can compute the probability of it being heads or tails, but it's always less than 100% and more than 0, no matter what you're computing. It comes out of the uncertainty principle that I said in the other view graph about not knowing your position and momentum. You can sometimes get a very good answer. So if you ask the question, what is the probability that I will flip this laser pointer, it'll go off to the Parthenon and come back to my hand again? The answer is not 0. Even though it's not allowed by laws of gravity, we have to go through the building and break. There is a very small chance it could happen. And this is observed. Atomic decay, the decay of most atoms, should not happen, except for quantum mechanics allows them to sometimes go through, which is why we have a half-life. Einstein had trouble with this. His famous quote is that God does not play dice with the universe. He thought that, and he was not the only one, he thought that it's just that humans are stupid. If we really did know everything about the atoms, we could predict what they do. And maybe we can't figure it out. Maybe the atoms aren't telling us, but the atoms know. So the atoms are following their own rules, and that's how it is. It wasn't until about 10 years after he died that we realized there was a way to experimentally test this. Those experiments were done, and they're still being done, but they all agree universally that physical quantities are not even defined until they're measured. They don't even exist. So God maybe doesn't play dice with the universe, but he doesn't pay too much attention to it. He lets them do what they want. You do the experiment, you make a measurement, you force it to make a decision, it will make one. This leads to the concept of a multiverse. Imagine you have something coming along here. There's an example here, it's called Schrodinger's cat, which is, what if you had a cat in a box and there was a radioactive element that had a 50-50 chance of decaying in a certain amount of time, and if that radioactive element decayed, it would release poison gas and kill the cat. But if it did not decay, the the thing would shut down and the cat would be alive. So you're here and you find, in this case, the cat's dead. Let me change that. It doesn't kill the cat. It puts the cat to sleep. So we've kind of the cat sleeping here. And you say, all right, well, the atom went off or didn't go off, and that's what happened. But maybe the universe split into two. And the other side, in the parallel universe, the cat is awake, and there's a parallel you that sees the cat awake, and you have no relation to this, so you think that's what happened. The multiverse says both of them happened. Can we prove that really both of them happened? The answer is maybe. Some people think they can do it. There are things called entanglement that can be interpreted that way. And I've recently seen a paper where a black hole-like, wormhole-like connection is established here. And that is how these two things can be communicating in some sense. So there are some people who say, yes, the multiverse agrees, and we even have a little bit of data to show that that's what's going on. So if the multiverse exists, let's ask, does every possible now exist? Everything that could happen? Does it happen? Because every measurement could go one way or the other, and there's a parallel world doing one and the other. In fact, the physicist Richard Feynman, who many of you know, showed that if you want to do quantum calculations right for how electrons work, you have to sum over all possibilities, no matter how crazy, and the interactions between them. So, to give an example of that, this lecture. I go home, back to America. My girlfriend asks me, how'd it go? Being a guy, I say, fine. Okay, now, what does that mean? In the quantum mechanical sense, does it mean that I lectured you really well? Or does it mean that I did such a bad job that you tried to burn me at the stake? You have to compute the probabilities of these things, and they go into the equations as if they happened, including the probability that these flames may have burned his clothes. It all goes in. So maybe all of these things do exist. If all of those things do exist, what becomes of our universe and what becomes of time? Well, we have multidimensional nows then. These are all nows that existed, and they can have in three-dimensional space and time. We have the events that Einstein talked about, which are sort of atomic clocks and proximity. Each event's a little different. What if we order them so the difference between consecutive events is minimized? We put some order together, we come up with a mathematical expression for when two events are very similar to each other, and then that order is space-time. This is my definition of time. It's consistent with my definition of time from the beginning. And modern art, you might make fun of modern art, you might like modern art, but it is known that Picasso and Duchamp, who did this one, were aware of the theories that were floating in the early 1900s. They were aware of relativity, they were aware of quantum mechanics, and Cubism, and all these expressions may have had some root in the new physics that was being developed. The last part is going to shed some doubt on the whole question now. There are things called virtual particles. What do I mean by a virtual particle? These are things that come out of nothing and they quickly disappear. You might say that's impossible. We have the conservation of energy. You cannot make something out of nothing. That violates all the rules. That not only did our mother tell us that, but our father told us that, and it's in all the equations. But they only temporarily violate the energy conservation, and the larger their energy, the quicker they disappear. That's actually quantum mechanics right there. And we know they exist because we've done experiments, which I'm not going to talk about. Some people have thought our universe might be a vacuum fluctuation. It started that way, and then because in a very super dense state it became a black hole, changed the laws of physics inside of it, and was able to keep going. And they think that our universe might even be spawning baby universes out of our vacuum that are breaking off and forming their own universes. Because if you make a large enough one, it can become a black hole and change the game. This is called the quantum foam. It exists at a level way below us, the decimal point 26 zeros in the 6th level. We are sitting on top of it. If you go down to there, space and time have lost their meaning. And we come to my last view graph. Remember I told you we'd see Professor Wheeler again. I heard him give a talk around in the 1980s. He said, are space and time accidents of nature? The color of an object is not a fundamental property. All green things are not the same. All black people are not the same. The color just depends on what wavelengths of light they happen to reflect. It's not what's really going on. So he thought that space and time might not be fundamental either. And especially in black holes and quantum foam, they have no meaning. If they have no meaning there, then it's just a human construct, so we can understand what's happening. When I first heard him give that talk, I thought he was totally nuts, and I told my colleagues about it. They can't be right. But now I think there might be something to it. So we've come to the end now. Although I haven't told you what time is, time's up.
Thank you, Dr. Matsakis, for the great. Ευχαριστούμε πάρα πολύ. Λοιπόν, να προχωρήσουμε γρήγορα σε ερωτήσεις, γιατί...